Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Research into fundamental phenomena can have profound implications for a variety of applications. Water in confinement behaves very differently from bulk water, and now new research shows why this happens. Using a type of surface-specific vibrational spectroscopy that can directly probe water orientation in a hydrogen bond environment, water confined in a cavity of 8 angstroms or less could be investigated.
We use this technique called some frequency generation in our study. An elegant aspect of that technique is that it allows you to look at the water directly, so you don't need to put in any probe molecules, through their intrinsic vibrations. It's a spectroscopy, and this spectroscopy has a selection rule that symmetry has to be broken in order for signal to be generated. And so that's of course true at interfaces and at both interfaces if the distance is large enough. But we will not be able to see whatever is in the bulk between these two interfaces if there is bulk. So now the question is, so we have now this spectrum of this confined water. Is that simply a sum of those two interfaces, or is more going on?
That was Professor Dr. Misha Bonn, Director of the Max Planck Institute for Polymer Research in Germany. Visible light and infrared spectroscopy were used, and both beam pulses were focused on the same point at the same time with enough intensity to detect a signal without frying the sample. The cavity was created by enclosing an electrolyte solution between a graphene sheet and a smooth calcium fluoride substrate under controlled relative humidity. The thickness of the water in the cavity was determined using both atomic force microscopy and ab initio molecular dynamics simulations of the graphene sheet. Tuning the thickness of the confined water by altering the relative humidity showed that when the water thickness is reduced to around 5 angstroms, the spectroscopy data changed significantly when compared to a water thickness above 8 angstroms. The results show that interactions with the interfaces dominate the water structure at the 8 angstrom scenario, with the central layer of water exhibiting a signal resembling bulk water. At 5 angstroms, nanoconfinement effects start to appear, with the water molecules starting to lie flat, parallel to the interfaces, and the hydrogen bonding network beginning to weaken.
That actually kind of makes sense, because as you go from 8 to 5 angstroms, you go from a triple layer of water to a bilayer of water. And we know that if you have a bilayer of water, the hydrogen bonded network likes to be in plane. So you get all these OH groups that were out of plane before, they tilt into the plane, and now you get a 2-dimensional network instead of a 3-dimensional network of hydrogen bonds. And so this explains everything that we're seeing. And then we go to further confinement, we see more exotic monolayer of water that we don't quite understand why it responds the way it does. But it means that this sort of critical thickness that we were looking for is about, somewhere between 5 and 8 angstroms.
Developing such a sensitive technique to measure the effects of confinement was not without challenges. Dr. Yankang Wang, group leader affiliated with the Max Planck Institute for Polymer Research, as well as Southeast University in Nanjing, China, and one of the lead authors of the study, explains the power of the sum frequency generation spectroscopic technique.
Very interesting to see that the SFT can probe such extreme thin water layer.
Different electrolyte solutions were used since water will experience ionization and release of ions from an interface. The results were consistent regardless of the electrolyte used. The ab initio molecular dynamics simulations, which are accelerated by machine learning, were important for validating the experimental results, allowing the behavior of the water molecules to be observed. The results mean that the properties of water can be tuned by modifying surface chemistry and have implications for microfluidic devices and more.
We can now explain this difference between graphene and graphite-based nanofluidic devices and hexagonal boron nitride-based devices, where people had seen orders of magnitude different friction, but had no explanation because everybody actually assumed that graphite and HBN are equivalent materials. So the conclusion from our work is that the interface must dominate what's going on in those devices. So we've then followed up and done the experiment where we looked at how does water interact with the HBN, and that is fundamentally very different from how water interacts with graphene. So there's charge transfer between water and HBN, and so this is not a neutral hydrophobic surface, but a very hydrophilic charged interface suddenly. And this explains why friction is so much larger for HBN-based devices than for graphene and graphite-based devices. So I think it has helped us better understand nanofluidics and nanofluidic devices. We're opening up a window to seeing inside these devices and learn what's going on. And then that, of course, has implications for desalination, for water purification, also for hydrogen generation.
In principle, we can design the material in a way that tune the water properties as we wish by tune the properties of the material itself. So we can in principle predict the properties of the water in between the material, and which I think could be important for many communities, including catalysts, or like Misha said, nanofluidics, and also could be important for ion transport.
This work was published in a recent issue of Nature Communications. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.